Hi, my name's Clare Burrage from the University of Nottingham, and what I want to talk about today is how we might search for dynamical dark energy fields with local experiments. So, what can we do on small scales to tell us about what's going on the very largest scales in the universe? So, just to outline what I'm going to talk about, I'm going to introduce dark energy, which I don't think I need to introduce to this meeting, and the dynamical scalar fields that might drive the accelerated expansion of the universe. And then we're going to talk about how that might lead to time varying constants, how that might lead to fifth forces, and then the role that environmental effects and screening can play in hiding or not hiding those variations and those fifth forces from detection in local experiments. So the motivation for dark energy, which I'm sure we all know, is that we don't understand why the universe is expanding in the way that it is today, in particular why the acceleration is happening at the rate that it currently is. An additional motivation or tentative motivation comes from the results of the DESI collaboration that potentially suggest, as shown here, that the equation of state of whatever this component is that is driving the accelerated expansion seems to be changing with time. Now, this talk is not about these results and how strong or not strong we should consider the evidence for that, but at least it's very much not a settled question whether or not there could be a dynamical component driving the accelerated expansion of the universe. So those are the results from DESI, just to say that this can also be seen in the results from the DES collaboration. Again, a slight tension, pulling W0 WA away from the cosmological constant value we would expect to see if there really is nothing extra dynamical going. So we introduce new light scalar fields, either directly to be our dark energy, so like a quintessence field, so a new light scalar whose dynamics are causing the acceleration and the expansion of the universe. They could also be not directly driving that expansion, that accelerated expansion, but rather some consequence of another mechanism that solves the cosmological constant problem and explains why the universe is expanding in the way that we see today. But the scalar fields also potentially come in slightly more indirectly if we say, well, actually, this accelerated expansion is a consequence of the fact that we don't think GR is the right theory of gravity on all scales everywhere in the universe. And if we modify our theory of gravity, that can often introduce new degrees of freedom, often Lorentz scalars, that we could then also try and look for. So, which again, either directly or indirectly might explain the accelerated expansion that we're currently seeing. So if we think that there are dynamical light scalar fields in our model of the universe, in our model of particle physics, then we can start to ask how we might see them. And that's really the focus of what I want to talk about. And in particular, there are sort of two things that we can ask. One is that if we have a field which is dynamic in the cosmological background, so it's evolving with time, can we see that time evolution locally with any kind of high precision test that we can do on Earth or in the solar system? And then also, if we have a dynamical scalar field, then fluctuations in that scalar field can mediate potentially new forces. And then we can ask as well whether we can see those new fifth forces in an experiment. So to start with the first question, can we see the time evolution? Obviously, to see time evolution, what you really need is a really good clock. And we are very lucky that nowadays with atomic clocks, we have spectacular accuracy. So typically the frequency doesn't shift of the atomic transitions. The frequency doesn't shift by more than 1 part in 10 to the 18. So really, really incredible precision. And if we have some new scalar field, as indicated here, so this is a scalar field which couples maybe some nth power of the scalar field, couples to standard model fields, so maybe the photon through F mu nu, F mu nu, or maybe some fermion here, an electron through the mass term for the electron. And if it has those interactions with matter, what that means is that what it looks like is that the fundamental constants are varying as the scalar field varies. And potentially, if we have different couplings to different standard model fields, then we can get different variations in different fundamental constants. So as we've shown on the slide, maybe the fine structure constant alpha might vary, maybe the masses of your fermions might vary, or maybe the QCD scale, what you think the QCD scale is, might vary. And what an atomic clock allows us to do is to ask whether these constants are really constant. And in particular, by comparing two atomic clocks, so two different atoms, whether transition energy is a slightly different function of those fundamental constants, because we've got a different atomic element. Then we can really start we have if you like, a reference clock and a probe clock, and we can ask if they're varying in the same way or not varying at all with respect to time. So this was considered in a nice paper last year by this group of people at Imperial. And this is a forecast of projected bounds that one might get on a quintessence type dark energy model over an observation time of about 3 years with atomic clocks of the kind that are currently being built at RAL. And so what you can see is the dark energy equation of state on the horizontal axis, and the coupling, the effective coupling of the dark energy scalar to matter on the vertical axis. And the constraining power depends on the type of atomic clocks that are being considered, and obviously on how much we think the dark energy coefficient of state deviates from -1. If it's truly -1 and it's just a cosmological constant, then we wouldn't see any time evolution. But nevertheless, this shows the kind of that we can, in principle at least, in the near future, really probe the equation of state directly with a local clock. If you don't want your scalar fields to couple differently to different types of matter, different fundamental particles, then there's still hope to see time variation, that you might, even if with a universal coupling, that you might be able to see that time variation through the variation or not of Newton's constant. So one of the best ways that we have of measuring this is lunar laser ranging. So what's shown in the image on this slide is a retroreflector, which is placed on the moon, and then bouncing lasers from Earth off the retroreflector and back allows us to track incredibly precisely the way the moon falls in the Earth-Sun system. And one of the things that provides us with is a very tight constraint on how much Newton's constant hasn't varied. Okay, so that's what's quoted at the top, that G dot over G has to be less than 0.008. Now this combination actually is G dot over G is one of the parameters that is often used in the linearized parameterization of dark energy. So this is the Bellini and Sawicki parameterization in terms of these alpha parameters. And that would be alpha m that is proportional to G dot over G. And it's commonly assumed, there are other choices available, but commonly assumed that the time variation is such that those alpha parameters are some constants times the fraction of dark energy. And the current constraints on those parameters, on that linearized parameterization from cosmology, so I'm showing here a plot from a paper from 2024 by Cyril, I hope I've pronounced that properly, Nolla and Schoen, and showing that we can put about an order 1 constraint on the Cm parameter, so the constant here. So that's much less good than we can do with lunar laser ranging, right? It's an order 1 constraint rather than 0.002 constraint. However, that linearized parameterization is linearized cosmological perturbation theory, so it's not at all obvious that what you're constraining locally really is the same thing as what is happening on large scales in cosmology. So the question arises, the fundamental question is, under what conditions can we say that the local time variation of the constants that we see is the same as the cosmological time variation? So this is actually something that I looked at a few years ago now with a really excellent PhD student, Johannes Dombrowski. And for scalar dark energy models, we were able to say that the cosmological time evolution of the fundamental constants implies an equivalent local time evolution if three conditions were met. That the local fifth forces are weak. Okay, that's a very easy condition to satisfy. If that's not true, you've probably got bigger problems to worry about. The most important criteria was that the weak equivalence principle had to hold. So the scalar field had to interact with all types of matter in the same way. And we also, our derivation required that the fifth forces are parallel to the gravitational forces. That was really so that we could actually do the calculation in a reasonable way. So the key condition here really is that if the weak equivalence principle holds for the dark energy scalar, then you would say that cosmological time evolution implies local time evolution, and we can use those constraints, for example, from linear laser ranging to constrain our dark energy models. So when does the weak equivalence principle hold and when does it not for dark energy theories? Well, that's a point I'm going to come back to in a minute. But for now, I'm going to move on to talking about fifth forces. So again, as we said, if we've introduced a dynamical scalar field into our theory of physics, then fluctuations in that scalar, if it interacts with matter, will mediate a new fifth force. And we've been looking for fifth forces, both in the experiment, in the laboratory, that's the plot on the left here, and in the solar system, that's the plot on the right, for a very long time, and we haven't seen any evidence of that. So where do we go from there? How is it possible that something that we want from a dark energy theory point of view, appears to be ruled out by experiments? Well, the answer there is really that those constraints that I showed on the previous slide, they are only on the simplest model of a scalar field and how it interacts with matter. Okay, so those constraints are on a scalar field with just a mass term, a linear and a canonical kinetic term, and a linear interaction with matter. But for a scalar field theory, we are allowed to consider things well beyond that. And those theories tend to be nonlinear, and they display a behavior that gets called screening in the literature. So that's the idea that because your theory is nonlinear now, that the properties of the fluctuations depend on the background. And that can mean that, for example, what you thought was your coupling constant describing how your scalar field interacts with matter might vary depending on the environment. And so it can be weak locally, so suppressing those interactions, but potentially in the cosmological, those interactions could still be significant. Similarly, you could arrange for your scalar field to have a large mass in a local experiment because of the behavior of the background. And so the force becomes much shorter range than you thought it was, and thereby invading your experiments. And you can also play with the kinetic structure of your theory. You have to be careful about how you do that, but you can do that. And you make the coefficient of your kinetic term very large, and that makes it very hard for the scalar field to propagate, and again suppresses the effects of the fifth force dynamically, so locally get suppression. And in terms of how that changes the fifth force around a macroscopic large object, there's sort of two different things that can happen. One is that we change the way in which matter sources the scalar field. So one lump of matter with mass m, maybe not all of that mass actually acts as a source for the scalar field. The other possibility is that all of the mass of the object sources the scalar field, but the behavior of how the scalar depends on the distance away from that object changes. Now, in the latter case, so if we're changing the dependence on distance, then all matter sources the fifth force in the same way. It's just that, it's not the 1/r fall off that you were expecting. And so those theories do satisfy still the weak equivalence principle. And so those are the theories that are still constrained by that time variation, local time variation of fundamental constants that we talked about before. If your theory, on the other hand, changes the way in which matter sources the scalar field, so different lumps of matter source the scalar field in the different ways, you have an emergent violation of the equivalence principle there. And so that those theories do avoid local time variation constraints, but then we still have to worry about whether we can detect or not the fifth forces. So the picture that we're thinking about here is because different types of matter source the scalar field in a different way, that the fifth force acts more strongly on some objects than others. And in fact, what happens is that the fifth force will act more strongly on less compact objects, so sort of typically smaller objects, than it will on larger or more compact objects. So that's the image that we have on the right hand side of the slide here. So that's what we're going to try and look for, is to see whether we can see these fifth forces that are acting that we may not see around large macroscopic objects, whether we can come up with suitably designed experiments to look for those fifth forces on small enough objects. Now, the archetypal example of a theory where this happens is known as the chameleon. So just to quickly introduce that to you here, this is a scalar field, canonical kinetic term. It has a potential and it has some interactions with matter, which now, because I'm thinking about macroscopic distributions of matter, I'm just going to write as rho m. So this is a non-relativistic matter, which I'm describing with an energy density. And the classic chameleon model has a potential, an inverse power law potential, so lambda to the 5/phi, and a linear coupling to matter, so that's that phi/m, and capital M is the energy scale controlling the strength of the interaction between the scalar field and matter. And the combination of those two things is what makes the mass of the chameleon vary with the local energy density. So in regions of high density, the field, the minimum of the effective potential, so the combination of those two, the red and the blue lines, shifts to the left slightly, and most importantly, that fluctuations around that minimum are much, much more massive than they are in low density environments. So this is the same thing said again in maths, that large objects and large and dense objects, the scalar field becomes very heavy. It becomes very difficult to source the scalar field inside, and so then it's only a shell of matter near the surface that acts as the source for the scalar field. So instead of the Yukawa form of the scalar that we saw on the previous slide, what has happened in this first expression is that there's an extra factor lambda a here for our object A, which is 1 for certain objects and very small for other objects. And that depends on this condition, whether the density times the radius of our spherically symmetric source of matter, whether that's bigger or smaller than this combination of the coupling constant and the background value of the scalar field. So there will be certain objects whose density and radius mean that lambda is 1, and this just behaves as the Yukawa force as we saw before. But there will be other objects where the density times the radius squared is sufficiently large, which mean that lambda is much smaller than 1, and our scalar field is suppressed, the fifth force is suppressed. And this is the thin shell screening of our scalar fields. And so ideally we're looking for experiments for which rho times r squared is a small number, and those would be unscreened from the fifth force. They would see the full strength of the fifth force, and we would be able to see them in a suitably designed experiment. So we have many of those in the laboratory, looking for equivalence principle violation, looking for short range forces. And this is the summary plot that we have. And in the last decade or so, the chameleon parameter space has really gone from being fully, almost entirely unconstrained to now being at the point of being arguably most of the interesting parameter space being nearly ruled out, in particular with these atom interferometry experiments. And so to summarise, what I've tried to explain is that we don't understand why the expansion of the universe is accelerating, But explanations for this often introduce light scalar fields that can mediate fifth forces and cause variations of fundamental constants. Screening can help hide some, but not necessarily all of these effects, and it also provides new opportunities for detection. Thanks very much.